Okay, good evening, everyone. Hope you're all doing well. We are going to move into chapter 3 today. We went over density, right, last week? Yeah, okay, good. I just wanted to make sure I'm teaching 4 sections and there's a mini master, there's an online, there's an in-person, and everybody's doing the same thing, but slightly different. So I'm always getting everybody confused. Sorry, it's not you, it's me. All right, so we're moving into chapter 3. We'll kind of say goodbye to math for a little bit until the end. Okay, so if we were to kind of look at the entirety of the universe, we want to break it up into 2 big categories. So one category would be matter, and then the other category would be energy. I think matter is usually a little bit easier for people to kind of wrap their heads around because it's tangible, something we can touch. A lot of times something we can see. Energy can be a little bit trickier, but we will work through it. Matter is the stuff of the universe. It's the meat. Energy is what makes it interesting. It's what allows matter to move and change, transform. So we need both of those things. As far as atoms and molecules in the room you're sitting in, everything that you can see is made up of matter. The type of matter that you're looking at is dependent on what's happening, what atoms are present and how they're combined with each other if they happen to be in a compound. Like over here in a picture, they've got water, and water has a certain set of properties because it's made of 2 hydrogens and an oxygen. I don't know why there's a golf club here, but there's a golf club, and that's made out of graphite, which is just carbon. Okay, and so it'll have a different set of properties. So what do we need in order to be classified as matter? It needs to occupy space and it needs to have a mass. Now, that can be a very, very small mass. It can be a very, very small volume, but it needs to have those 2 components. A lot of things that you can see, or not a lot, all the things you can see do contain matter. There are, other types of matter that you can't see. And we live in our minds are so humanist, right? We think on our scale and what we can perceive. And so, we forget that in the air around us, there's matter and material and dust. There's stuff that's very, very tiny that we can't even see with like a microscope. We'd need an electron microscope in order to see it. So know that you can't always perceive the matter that's around you. So if we were to take matter on a human scale, a macroscopic scale, because we're humans and we live on the human sized scale, we look at matter and sort of assume that it's continuous. Like when you run your hand over a desk, it feels like it's one continuous solid piece of material, but that's not actually what's happening. Matter and its more fundamental parts is really discontinuous. So if we were to take like, let's say we took a hunk of gold and we cut it in half and we cut it in half and we cut it in half. When we start to get down to the microscopic scale, there's actually quite a bit of space between adjacent atoms. It's not this smooth, continuous sort of thing. But its most fundamental component for an element is going to be an atom. If we had a compound, like let's say we have a bottle of water and you cut the water in that water bottle in half and half and half and all the way down, its most fundamental form will be a molecule. And that molecule will be 2 hydrogens and an oxygen. And it'll have a very specific geometric arrangement and relationship to the other atoms that give it its properties. So recent advances in microscopy has allowed us to image atoms. Yeah, so there are some ways that we can now image an atom. We're not actually seeing it, we're just seeing a computer's representation of what's there. So looking at an aluminum can is made up of just aluminum atoms stacked together in solid form. These aluminum atoms exist as independent particles. They're not like chemically bonded to each other. They're just in a solid form where they're aligned in a unified arrangement. Now, if we look at this thing over here, isopropyl alcohol is a compound, meaning its base unit, if we were to break it down, would be a molecule. So instead of it just being a single atom that identifies aluminum, right, we now have this isopropyl molecule. That's going to be the fundamental thing that we can still classify and would still have the properties of the overall material. If I was to take one of these little molecules here and break them apart, I could break them apart into carbons and hydrogens and oxygens, but they would then lose the original property of the isopropyl alcohol. So here's a scanning using a tunneling microscope of nickel atoms. So what we can see here are the nickel atoms, they're all lined up, and there's these divots in between them where there's empty space, because again, matter isn't this smooth, continuous thing, even though on a human scale, it does feel that way. Here is a, looks like this is an image of DNA. We can sort of see the double helix in there. Again, lots of space between adjacent atoms in the molecule. So when looking at matter, anything that occupies a certain amount of space and has a certain mass, we can distribute it into 3 states, being a solid, being a liquid, and being a gas. Now there is a 4th state, which is plasma, and actually quite a bit of the universe exists in this plasma state. But in order for that to happen, we have to have very, very high temperatures. So it's not something that we interact with really on a daily basis. You may see plasma in the sky if there's like a lightning storm or something like that. But really, we're going to just focus on solid, liquids, and gases. Okay, so a lot of times when we write a chemical formula like H2O, we like to give it a state as well. So we'll say H2O with a little S next to it because it's a solid. Water is one of the few substances that can exist as a solid, a liquid, and a gas all simultaneously at what we would classify as room temperature, right, or our Earth standards. In ice, which is the solid form of H2O, the water molecules are closely spaced. And there is vibration, there is thermal energy. We're not at like absolute zero, so it's not completely frozen. There is some vibration happening. But the vibration between adjacent water molecules is so small that it doesn't allow them to break apart. So you can kind of think of these water molecules as like soldiers in a line or friends in a line, and their arms are all looped around each other. Okay, so they're hooked onto each other, and that gives them this fixed arrangement. Now, if we move into a liquid form, we want to go from ice to water. What do? We add heat. We put thermal energy into the system. And what that does is it causes the water molecules to vibrate. Okay, and so now they're vibrating faster, and that hook that you had on your buddy next to you is no longer stable. So you'll actually lose that attachment or that arrangement, and now you and your buddies can flow past each other. Now you're still in a very small space, so the volume doesn't change. You're still contained in a tiny area volume, but you now can roll past each other. So that's what gives liquid that fluid quality, right? It can change its shape if you pour it into a different container. If we add even more thermal energy, even more heat, we get steam. And in this case, the water molecules, the H2O molecules have so much thermal energy that not only are they rolling past each other, but they're also separating from each other. So they're taking up a bunch of space. It's just too hot for them to be right up against each other. So now we've got these water molecules that are actually acting independently. They're not even like clumping together like a liquid does, right? It kind of groups itself together. They are just expanding out. And so because of that, gases can assume not only the shape of their container, but they can also assume the volume of their container. So of the 3 states, gas is the only one that we can expand and contract the volume, or we can compress a gas. We cannot compress a solid, and we cannot compress a liquid. So here's a sort of, these are microscopic images of what's happening with the water molecules. closely packed together, and they're all lined up, okay? And the liquid, closely packed together, but they're not lined up. They have the freedom to roll and flow. Here, not closely packed together and not lined up, okay? So kind of gone all over this, but in a solid, the neighboring atoms are fixed. So because of that, they'll have a fixed volume and a rigid shape. So if I take a hunk of diamond and I put it in a cup and then I pour it onto the table, it's going to keep the same exact shape and the same exact volume. Nothing changes on it. Most of the metals that we see on the periodic chart are in solid form at room temperature. Mercury is the only one of the metals that will exist as a liquid at room temperature. We can divide solids down into being either a crystalline solid or an amorphous solid. So a crystalline solid is when you have a long range order. So let's say it's an army of 50,000 soldiers and they're all facing the same direction, very, very strict. All right, the amorphous solid is going to be like 50,000 high school students. So there's 3 of them facing in one direction and then maybe 7 facing another direction, and they've kind of made these groupings. So we don't have an overall long range order. They're still fused together, but they aren't as neat as the crystalline one. We can see a picture here where, there we go, there's like the soldiers in the army, right? All nice and lined up and neat. Here we've got, you know, they're staying in their spot, but it doesn't have any long range order. Crystalline structures will be things that have really nice 3-dimensional structures like diamond, table salt, sugar, things like that. Amorphous solids are going to be things like rubber, glass, plastics. They tend to have more of this amorphous, or they don't have the long range order. There's our table salt. If you see something on the human scale that looks like this, it's very like, it has very nice cleavage. It's grown into these really pretty crystals. You can pretty much assume that it has that same sort of neatness on the microscopic scale. So a liquid, right? We've added heat. Now the molecules aren't fixed. They're still in a small space though. So if I take 100 milliliters of water in a cup and I pour it into a graduated cylinder, it's going to still read 100 milliliters. Doesn't matter what container you put it in, it will have the same volume, but its shape changes, right? So if we put it in a beaker, it would be, you know, kind of wider. If we put it in a graduated cylinder, the water would be a little bit taller. Volume stays the same, the shape changes. Water, gasoline, alcohol, mercury, all examples of liquid. And then gas, because they have even more thermal energy, there ceases to be any sort of interaction between the molecules. So they like to spread out, which means that they will not only change their shape to the container they're in, but they'll also change their volume to the container that they're in. And that works in both directions. So you can take a large quantity of gas and compress it down, like you would see in like a canister of whipped cream, or if you use like some sort of scuba tanks going scuba diving, right? You've got oxygen, nitrogen, you've got it compressed down so that you have more time in a smaller space. If I took a canister of compressed gas and opened it in the room I'm in right now, the gas will leak out and then it will disperse to fill the entire room in an even distributed manner because the particles don't clump together. So they're going to stretch out. And then if I was to open the door, it would spread into the rest of my house. And if I was to open the windows, it would disperse into the atmosphere. Oxygen, helium, carbon dioxide, all examples of gases. I don't expect you to have every gas memorized, but do know oxygen, helium, carbon dioxide, some of the basics. Know that those are gases at room temperature. Here we've got 2 pistons, and the top one, there's a solid, and we could also, instead of a solid, put a liquid in here, and there's no room for compressibility. On the other hand, if we have a gas, we can push down on the piston and compress the gas. You guys experience this every time you fill up a bike tire and you use a bike pump. When you press down, you start to get some resistance because you're packing more atmosphere into a smaller volume. So this is a good chart that kind of sums everything up. Know it, just know how shape, volume, and compressibility are affected by the state that you're in. So when moving forward here, we're going to now that we kind of know what matter is and we know the different states we can have for matter, we're going to classify matter even farther, because it's not enough to just say, oh, I have matter. Okay, well, what kind of matter do you have? So I'm going to jump forward here in the slides because I like to see this first. So matter is going to be at the top, and we're going to break it up into two different categories. On the left here, we have pure substances. On the right, we have mixtures, right? And then if I go for my pure substances and I break that up, I can break it up farther into elements and compounds. Okay. Mixtures can be broken up into homogeneous mixtures and heterogeneous mixtures. We will go through what all these things are, but I think this is kind of a nice place to start. I wish they put this slide at the front. So matter, what do you have to be? You've got to have mass and you've got to take up space. Matter can be a solid, a liquid, or gas or plasma, but solid, liquid, gas for now. So let's go back to the first part here and just talk about what the difference is between a pure substance and a mixture. So a pure substance is going to be composed of only one type of atom or one type of molecule. Okay, you have to be able to write a chemical formula for a pure substance. So helium, right, or water, H2O. Those are examples of pure substances. A mixture, on the other hand, is composed of two or more different types of atoms or two or more different types of molecules that are just combined together in the same canister. Okay, they're not necessarily fused together. That means that you can change the proportionality. So like salt water, I can add more water, I can add more salt. Is there a specific chemical formula for salt water? No. We know what it contains, but I don't know what the proportionality is. You'd have to give me a concentration for it. So let's break up pure substance a little farther. We're going to break it down into element and compound. An element is a pure substance that can't be broken down into any simpler, I want to say simpler identifiable substances. I could take a carbon atom and break it down into its protons and its neutrons and its electrons. But the protons that are in carbon are the exact same protons as the ones in hydrogen or, magnesium. So they're those fundamental building blocks, those subatomic particles, are the same no matter what. So if I took a hunk of carbon and I broke it down, its simplest identifiable thing would be a carbon atom. As far as elements are concerned, there's no chemical transformation that can decompose an element into simpler substances. Now, if you've ever done any sort of nuclear chemistry stuff, yes, you can take something like carbon and decompose it into a different material. But we're not doing nuclear chemistry for this class. We're only going to be dealing with chemical transformations. So as far as we're concerned, if it's an element, it's going to stay that element. Where are all the elements? They're on a periodic table, periodic chart. There's one in the back of your lab manual. There's also one in the textbook, and you can find millions of them online. I definitely would have a periodic chart printed out. I'd have one physically available. Definitely by next week, because when we start lecturing on the periodic chart, you're going to want to be able to take notes all over it. You're going to have one periodic chart that you just is your best friend you love for the semester because it's going to have all your little cheats on it. So you want that. When you look at a periodic chart, there's like 120 or so elements. The first like 90 are what we call natural. The latter ones are synthetic. Natural because they exist in nature, synthetic because we created them in a lab, but maybe they exist somewhere in like very extreme circumstances, like in a black hole or something, we don't know. All right, so here is an example of a elemental pure substance, helium. We've got balloons here and they just have helium atoms in them. The helium atoms aren't combined with anything else. You can see that they're just by themselves. They don't have little buddies or anything like that. So we would say that this is an element. A compound, on the other hand, is a pure substance, and compounds and mixtures are where people sort of get things mixed up. A compound is a pure substance that has two or more elements, but they are in a fixed, definite proportion and they're chemically bonded together. So compounds, you can write a chemical formula like H2O, okay, or NaCl, or CaCl2, right? All sorts of different compounds. How many compounds are there? So many. They're making new ones as we speak, right? There's probably a bunch that'll be created by the end of this lecture. Compounds are more common than elements, just because most of the elements on the periodic chart are relatively unstable. They don't really like to be by themselves, so they do better when they're fused to something else. Water, table salt, and sugar are all examples of compounds. These are everyday names, right? How do you learn those? Memorization, okay? Water, I want you to know is H2O. Table salt, I want you to know is NaCl. All the rest of them, in chapter 5, I will give you a system on how to name compounds, all right? It won't be a memorization thing. It'll be if you know the system, you know how to name most inorganics. Compounds are different than elements in that a compound can be decomposed into a simpler substance. So I could take water, I could run it through a little contraption with a battery, and I could actually break it apart into hydrogen gas and oxygen gas, okay? So we can break them down into their elements. Once we get to the elements, then we can't really break them down any further and still be identifiable. So here's water. The hydrogens and oxygens are in a definite fixed proportion. If I add more water to, let's say, a container, it's still going to be 2 hydrogens for every 1 oxygen. That is the signature of water. If we changed it to 3 hydrogens for every 1 oxygen, H3O, that would be a different material with totally different properties. It wouldn't be water anymore. So whereas a compound, these different atoms are chemically united, they're bonded together. In a mixture, you have 2 different substances, but they're not chemically bonded. They just happen to be in the same container, okay? So they can be separated out from each other, like salt water, for instance. I can take the salt out of the water through a couple different processes. So some examples of mixtures, we've said salt water already. Here's little water molecules, and you can see the little salt, the NAs and the CLs floating around. The air is also a mixture. A lot of times people think of air as, oh, it's just oxygen. No, actually the majority of what you're breathing in is nitrogen. Only about 21% of it is oxygen. And then there's some traces, argon and methane and CO2, things like that. But yeah, it's a mixture. We can have gas-gas mixtures like this. We can have liquid-solid mixtures. We can have solid-solid mixtures, all sorts of different things. So when I divide mixtures into their 2 subcategories, we're going to have a homogeneous mixture, or sometimes referred to as a homogeneous mixture, and then we have a heterogeneous mixture. So the roots here, homo meaning the same, hetero meaning opposite or different. So homogeneous mixture is evenly mixed. Salt water is a great example of a homogeneous mixture. If I sample that salt water from the top of the container versus the bottom of the container, we're assuming that the salt is evenly distributed, evenly mixed throughout the material. A heterogeneous mixture are going to be 2 things that are mixed together, and like one thing sort of clumps in one area. Okay, so hydrocarbon and water. If you're like, what is a hydrocarbon? Oil and vinegar dressing, right? It doesn't matter how much you shake it. At some point, it's going to separate back out, and you can never get those little oil globulars to really disperse. Bananas and oatmeal, right? That's a good heterogeneous mixture. Some bites have more banana, some bites have more oatmeal to them. Looks like, yeah, so here we've got a couple examples. So an element here, I can't read the bottom. Oh, it doesn't even have anything. All right, well, this looks like, let's go with copper. Okay, so these are copper atoms all lined up. Here we have table sugar. Table sugar, it's going to break down into these sugar molecules, pretty clunky molecules. We would say this is a compound. Can you write a chemical formula for sugar? Yes, you can. You can. Over here, we've got a mixture. This is a homogeneous mixture, so T. Can you write a chemical formula for tea? No, tea is an art form, right? Everybody likes their tea a little bit different. Some people like it steeped a little longer. Some people like sugar, milk, whatever. And you can change those proportionalities up depending on what you want. A heterogeneous mixture, here's our hydrocarbon. When they say hydrocarbon, we don't go into organics, but a hydrocarbon is just something that has carbon and hydrogen. It's an organic material. It's an oil or a fat or something like that. So we've got our hydrocarbons sitting on top, and then we've got our water molecules sitting on the bottom. The reason the water is sitting down farther is because it has a higher density, so the oil floats on top. So you want to be able to identify something under what it would be. So I could say, hey, you know, air, what type of matter is that? And I don't want you to say it's elemental. Okay, I would want you to say it's a homogeneous mixture. So let's move on. So depending on what matter you're looking at, like what are the atoms and how are they arranged, they will have certain physical properties and chemical properties. Water has its own set of physical and chemical properties versus gasoline. A physical property is going to be a property that something displays or exhibits without having to change its composition. I know that sounds kind of weird, but like when you look at a gold ring, the color, that yellow color, it doesn't have to become something new in order for you to see that color. That's just something it innately has. Density is a physical property. Odor is a physical property. Luster is a physical property. Hardness of a material is a physical property. Shape is a physical property. Okay. A chemical property, on the other hand, is something that a material or a substance can display only through the process of changing its composition. So gasoline is liquid. The fact that it's a liquid would be a physical property. Gasoline is flammable. Its flammability would be a chemical property. In order for it to express its flammability or display it to you, it would have to undergo a chemical change. It would become something new. When you run gasoline through your car, right, you don't have like a bunch of gasoline when your tank's empty. What does it do? It produces heat, and then it releases CO2 and H2O out of the back of your car. So they used gasoline here. They use odor. Odor is a physical property and flammability is a chemical property. In actuality, octane, the thing that runs your car, is odorless. They put an indicator in gasoline to make it smell, just so you know. So the atomic or molecular composition of a substance does not change when the substance displays any of its physical properties. Anytime you go through a phase change, and when I say phase change, think phases like solids, liquids, and gases. Anytime you go from a solid to a liquid or a liquid to a gas, you boil, you freeze, you sublimate, any of those are not chemical changes. Those are just physical changes. I know that the materials can sometimes look totally different, right? Like ice and steam look completely different. You can't even see the steam. And ice is this like solid cold thing, but they're still H2O. So on a fundamental level, they are still the same material. They're just arranged differently. Their molecules just happen to be arranged differently. So when water boils, it changes from a liquid to a gas, but the gas is still H2O. All right. So boiling points, like the boiling point of water is 100 degrees Celsius. That's a physical property, not a chemical property. Here's the little water molecules down here, and here are the water molecules up here. They're both water molecules. These just happen to be farther apart, moving faster. So any state changes are always physical changes. So what is a physical change and a chemical change? Well, it goes along with physical properties and chemical properties. A physical change is a change that matter undergoes, but it changes its appearance, but it doesn't change what it actually is. So phase changes are a great example of a physical change. Iodine, when it's solid, it is like a gray metal. When it is a gas, it's a purple color. All right, it's really cool when you heat it up. It looks like something magical and chemical has happened. It's not. It's still the same material. It's just gone through a physical change. A chemical change, right? The matter will change its composition. So if I take copper and I leave it out for long enough, it'll start to turn green. It gets that patina color to it. That's a chemical change because it is literally stripping oxygen out of the air. And now you have a new material of copper oxide. So that would be a chemical change. So any sort of like tarnishing, patina, rusting, those are all chemical changes. Another example of a physical change, like taking a piece of paper and tearing it up into little pieces. Okay, I'm not changing what it is. It's still paper. It's just in a new shape. Now, if I took those little pieces of paper and lit them on fire, that would be a chemical change because you can't go back, right? Can't get back what you started with. Here's a nail. Okay, there's the iron atom sitting up here. This structure of just iron is relatively unstable. So it'll strip oxygen out of the air and create rust. Now, iron by itself is very cheap. That's why we have iron nails and they rust. If you want to get something that's galvanized, it will have iron combined with other materials so that it doesn't rust. All right, if we do undergo a chemical change, we represent it using a chemical reaction, and we're going to spend an entire chapter on chemical reactions. So don't stress too much about this right now, and you may have seen a chemical reaction before, but the way that it looks like, you read it like a book, left to right. On the left side will be your reactants. You have to have at least one reactant, okay? Then you'll have an arrow that separates your starting reactants from your ending products. And on the right will be your products. You have to have at least one product, and you can have more than one product, okay? Sometimes above the arrow, you'll have like little symbols like deltas for heat or an H+ for acid, or you might see stuff up here. An example of a chemical reaction, I will write one out here just to get comfortable with it. You don't have to like have this memorized or anything, but methane, where am I? Okay, methane, CH4, not CH3, CH4 plus oxygen produces CO2 and H2O. A lot of times they put the symbol for the state. So these are all in gases. So you'll see a little G at the end. Again, we will go over this stuff. And then I'm going to balance it. So I'm going to put a 2 here and a 2 here. So in this equation, the reactants would be this thing here, this CH4, which is methane, and this thing here, which is oxygen. The products would be CO2 and H2O. The arrow in between is that transition from your starting things to your ending things. Again, if you don't have a reactant, no reaction has occurred. If you don't have a product, no reaction has occurred. All right, gosh, these slides really just try and nail home the idea of a physical change and a chemical change. A physical change, you'll have the same substance, no new substance. In a chemical change, you'll have a completely new substance. Gosh, okay, a butane lighter. So if you just push on the plunger and you don't strike this thing, all you're doing is vaporizing the liquid butane into a gas. You might smell it, but it's still butane, right? Just a phase change. Now, if we hit the plunger whilst also striking it, we start a chemical reaction here, and these little butanes turn into CO2s and H2Os. These are different molecules than the starting thing, so we know chemical change has occurred. If your eyes could see atoms, it'd be really easy to tell that a chemical change has occurred, right? But our eyes can't do that. So we have to look for secondary things that tell us a chemical change has occurred. If light is produced, if heat is produced, if it gets really cold, like you have two liquids at room temperature and you put them together and they get really, really cold, it's a good indicator that chemical change has occurred. If like gases start to get produced, I pour two things together and it starts to fizz, okay, that's a good indicator. What are some other, if a precipitator forms, like I put two things together and all of a sudden I get a solid from two liquids, that's a good chance that there's a chemical change occurring there. And we'll spend more time later on in the semester going over that. So if I have two materials that are mixed together, like salt water, for instance, I can separate those through physical change. So I can take, let's say we have salt water. I can boil the salt water. I can boil the salt water, and the water will evaporate, and then we can collect it in a like receiving flask here and use a condenser. And then what will be left behind will be the salt. So mixtures can be separated through physical changes like heating and cooling. We can also separate some mixtures using filter paper. If the chunks are in it are relatively large. We can also separate through like osmosis or reverse osmosis, which is kind of like filter paper, but it's really, really teeny tiny. Okay, so next thing, law of conservation of mass. So there is no new matter. Matter is not created and it's not destroyed in a chemical reaction. Now, in nuclear reactions, you can have changes in mass. So what happens in nuclear reactions, mass will actually turn directly into energy. We don't talk about that. So for the sake of our class, we're staying in this realm here of chemical reactions. The amount of stuff you start with needs to equal the amount of stuff you end with. If I have a big log of wood, let's say it weighs 30 pounds, and I burn it in a vacuum, the mass in that vacuum in that room that's sealed off will still be 30 pounds. Okay. A lot of times we think, oh, I burned it, it disappeared, right? It's gone forever. No, it's not gone. When you have a fire, the wood that you collected, all that heavy wood you carried, it has now gone into the atmosphere. It's turned into CO2 and H2O. And it's a direct mass to mass relationship. So if you burn 30 pounds of wood, you've put 30 pounds of gas, CO2 and H2O into the air. Look at this little thing here. It says, suppose that we burn 58 grams of butane in a lighter. It will react with 208 grams of oxygen to form 176 grams of carbon dioxide and 90 grams of water. So they don't even write it a chemical reaction using formulas. They just say, hey, what am I starting with? I'm taking butane and reacting it with oxygen. So there's my butane and there's my oxygen. Right? I'm going to produce carbon dioxide and I'm going to produce water. Now, the two amounts for my butane and oxygen here is 266 grams when I add those together. Well, my carbon dioxide and water better also equal 266 grams. That is right there, the law of conservation of mass. Whatever you start with has to equal with whatever you end with. You're not getting rid of atoms, you're just rearranging them. Okay, we're just rearranging them with new partners in a chemical reaction. Let's see. Okay, so that first part there, it was all on matter. Now we're going to move to energy. The behavior of matter, why matter does anything interesting, is because of energy. Energy is just as important a component in the universe as matter is. When I say energy, I mean something's a capacity to do work. And when I use the word work, I don't mean it like in you're going to your job sense, even though that is work, it does require energy. But I mean work in the physics sense, defined as the amount of force acting over a distance. So if you have a lot of force over a very short distance, that's a lot of work, right? If you do a little work or a little force over a long distance, that's low work, right? The behavior of all matter is driven by energy. So anytime something moves, anytime something changes, anytime you have any of these like interesting things happening, it's all because there's energy behind it. But we can't really always see the energy. We see the secondary results of it. And just like the law of conservation of mass, there's the law of conservation of energy. And the law of conservation of energy states that energy is neither created nor destroyed. So within the universe, we have a certain amount of energy and that stays consistent. All that happens is the energy gets transferred from one thing to another. So, you know, you ate a peanut butter sandwich that put energy into your body, and then you like pushed your neighbor and they got flung across the lawn. You've transferred that energy. I don't know why you would do that, but you know, transferred that energy into your neighbor. They now have kinetic energy. if you push your neighbor hard enough and they hit the ground, their movement energy is actually transferring into a small amount of heat that's being moved into the ground. If you're like, no, there's no way that they're releasing heat into the ground. Well, think about something much bigger moving much faster, like a meteor. If a meteor comes down, it has a lot of movement, a lot of kinetic energy with a high velocity. It hits the earth, it creates a lot of heat. Energy can't just come out of nowhere, and it can't just vanish into nothing. That's why perpetual motion machines are not a real deal thing, because we can't just pull energy out of nowhere. Some different types of energy, there's all sorts, but for this class, you do want to know kinetic energy. So kinetic energy is the energy associated with motion or movement. So think like kinesiology, the study of body movement, kinetics, certain kinds of exercises, right? When something is moving, it has energy to it. The faster it's moving, the higher its velocity, the more energy it has. There's this other type of energy called potential energy. This is the energy that's associated with its position or a material's composition, its chemical composition. Potential energy is like stored energy, okay? So if I take a spring and I crunch it together, that spring has a bunch of potential energy. I've used my kinetic energy from my hands or my arms to push that kinetic energy into the spring. It's then stored in the spring. And if I release the spring, it'll kind of boing out and release energy into the environment. We have electrical energy, the energy associated with the flow of electrical charge. I'm not very good with electrical energy, so go talk to an engineer about that stuff. Thermal energy. This is the energy associated with the random motion of atoms and molecules. All materials, all atoms vibrate. The amount of vibration they have is directly related to the thermal energy. So if you put more thermal energy into something, they vibrate more. That's why we phase change as we get warmer. Chemical energy, that is a type of potential energy that's associated with the position of atoms in a chemical system. So certain things have more energy to them than others. Certain food that you eat has more potential energy than other foods. Things like TNT have a lot of potential energy. They want to break apart into something more stable. So for the unit of energy, the SI unit for energy is the joule, which is a capital J named after James Joule. The joule you can plug into your SI prefixes. Okay, so we can have a kilojoule, we can have a millijoule. So that's a good base unit. Another unit of energy out there is the calorie. The calorie can also be put as a base unit in your prefixes. Do you see how this calorie here has a lowercase calorie? It's a little c, lowercase c. That is not a nutritional calorie, okay? When you think of calorie in food, not the same thing. This little c calorie, you need 1,000 of these to become a nutritional calorie, okay? So sometimes the big C calorie is called a nutritional calorie, or sometimes it's called a kilocalorie because it's 1,000 of these little C calories. Why is there this thing called a little C calorie? What is that? That's the amount of energy it would take to raise 1 gram of water 1 degree Celsius. So if I had a little gram of water and I wanted to bump it up by 1 degree Celsius, I would use exactly 1 little C calorie to do it. Then we have a kilowatt hour. A kilojoule per second times 300 or 3,600 seconds in an hour. Okay, I don't spend time with kilowatt hour. Again, things with like electrical energy, I just sort of stay away from. But you do want to have these conversion factors available. We will use them. So, you know, again, how many conversion factors are there out there? So many. Hopefully you've got that system down now. So let's see, we've got 1 little C calorie is equal to 4.184 joules, and we'll see that number again. 1 big C calorie is equal to 1,000 little C calories, okay? Or we can call this thing a kilocalorie. And then we've got a kilowatt hour is equal to 4.6 times 10 to the 6 joules. And I don't spend a whole lot of time with that. So make sure you have these written down. somewhere because I want you to do a problem using these as your conversion factors. All right, so I have a candy bar and it has 325 big C calories in it, okay? Big C calories. I want you to find how many joules of energy are in this thing. Use your dimensional analysis, okay? And do note that this is a kilocalorie or big C calorie. I'll give you guys about 2 minutes to mess around with that. Okay, so for this problem, we are starting with a nutritional calorie or a large C calorie, and we want to end with joule. Now we need to take a pit stop in the little C calorie here. All right, so it becomes a double problem. So we go big C calorie to little C calorie and then little C calorie to joule. Big C calorie, what do we have? 325 of those. So I'm going to chain my conversion factors together. If my big C calorie is on top, I'm going to put the big C calorie on the bottom and then the little C calorie on top. If you want, you can underline the big C calorie just to remind yourself that you're looking at something different. Big C calorie, one of those for every 1,000 little C calories. The big C calories will cancel and we'll be left with little C calories. So we took that first hop. Now we want to go from little C calories to joule. So little C calorie was on top. Now I'm going to put little C calorie on the bottom because I don't want it anymore. And I want to put joule on the top. 1 little C calorie is equal to 4.184 joules. All right. We're going to end up with a relatively large number. There's quite a few joules in a candy bar. So we take our 325, we multiply it by 1,000, and then we multiply it by 4.184, and we get, okay, 1,359,800. the units on this being a joule. I'm going to start moving forward when we work on problems. I'm going to start rounding as is. Okay. I'm not going to write them out and then round for you. So this gets 3 sig figs. So 1, 3, 6, 0, 0, 0, 0 joules, or we write it in scientific notation, 1.36 times 10 to the 6 joules. All right. Maybe if they wrote things on candy bars in joules, we'd eat less of them. Probably not though, right? In Europe, they do put things sometimes in kilojoules. Good with this? Feel okay? It's nothing like earth shattering. It's the same thing as chapter 2. It's just a new conversion. Nice for you guys because you're in the online format. You get to have these. You can have these unit conversions and stuff like that available for you. So I would just have them sort of concentrated in one place, a formula sheet, something that's really easy to access. So you don't have to be like flipping through your textbook. Okay. They have another one here, a candy bar. Okay, this is exactly what we just did. So if you want to do another one, this is a smaller candy bar. You can go through and practice that on your own. A weight that's brought to the top of a building. Who's going to bring that weight up to the top of the building? You're going to bring that weight up. How are you going to do it? You're going to sweat to do it, right? You got to put some energy into that. So you're using your kinetic energy to move this weight up to the top of the building. Where has that energy gone? Well, it's transferred into the weight. That weight actually has now potential energy. It has more potential energy at the top of the building than it did at the bottom of the building. Because, you know, we're all experiencing gravity. And when you pull it up to the top of the building, it now has a space to fall. When it falls down, that potential energy that you put into the weight is now turned into kinetic energy. So the weight is moving down. It's got movement to it. Hopefully you're not standing underneath it. You will definitely feel that kinetic energy. If nobody's standing underneath it, where does that energy go? It transfers into heat into the ground. So you could actually register the temperature of this concrete going up just slightly. Chemical changes, potential energy, right? Yeah, so there are certain materials that have a high amount of potential energy because of their chemical makeup. TNT is one of those things. Things that have high potential energy like to go in a direction that makes them lower potential energy. So that weight wants to fall down. Mountains want to weather to the ocean, okay? TNT wants to explode because having a high potential energy is kind of unstable, right? A spring that's all coiled up real nice and tight, it wants to relax. When we have a chemical reaction, it is important to note that we classify chemical reactions as either being exothermic or endothermic. So in an exothermic chemical reaction, you have reactants that have a lot of energy. And then it releases energy and you get products that have a lower energy. Okay, this feels kind of, I don't know if this, I feel like this feels more intuitive a lot of times. So you have reactants, your starting thing, have lots of energy, your products have lower energy and you release energy. How does that energy get released in an exothermic reaction? Usually it gets released through heat. Okay, so the temperature will go up. Hence the exo, it's exiting. Energy is exiting the system. An endothermic reaction, because if we only had exothermic reactions going on in the universe, at some point, all reactions would stop, right? So we have to have something equal and opposite to that, which is the endothermic reaction. In an endothermic reaction, your reactants, what you're starting with, actually has a low amount of energy. And the products, what you end up with, have a high amount of energy. So the materials are stealing or absorbing energy from the surrounding environment. Endo, it's entering, okay? A lot of times these things will feel cool or cold to the touch. They feel cold. Like if you've ever had one of those ice packs that are room temperature and they've got a container and then a container and you break them, right? There's like an internal baggie inside another baggie, and you crack the internal baggie open, and all of a sudden it gets really, really cold, because what's happening is that there's a chemical reaction going on in there that is endothermic. So it's stealing heat from its environment. And if you're holding it, it's stealing the heat from your hand, or it's stealing the heat from your inflamed knee, or whatever area is like super warm on your body. So with all this talk of energy and heat and all this, we got to talk about thermal energy. So thermal energy is the constant random motion of matter. So all materials have thermal energy. We can measure thermal energy, or we can measure this random motion using temperature. So when I say, hey, it's 72 degrees outside, I'm measuring the thermal energy of the air. If I say, hey, it's 85 degrees outside, that means that there is more thermal energy to the air. The hotter an object is, the greater the random motion is. Okay. Now, heat is another word that we want to get clear on, because people get heat and temperature mixed up a lot. They think, oh, heat and temperature are the same thing. Temperature is the measure of thermal energy. Temperature is going to be measured in degrees Celsius, degrees Fahrenheit, or Kelvin. Heat, on the other hand, is going to be measured in units of energy. So heat is going to be in joules or calories. Heat is the transfer or the exchange of thermal energy caused by a temperature difference. So when a piece of cold ice is dropped in a cup of warm water, thermal energy is transferred from the water to the ice cube. Or if you have, let's say, kind of think of temperature as like specific to the object. Heat requires two things, an internal and an external system. So you have a pot of boiling water. That's the temperature of the water would be 100 degrees Celsius. If you stick your hand in that boiling water, there's a certain amount of heat that's getting transferred to your hand. That's going to be dependent on how long you leave your hand in there for. Probably not going to leave it in there for very long. So the transfer of that thermal energy is heat. What are the things we use to measure temperature? Fahrenheit. Again, faulty British system with Fahrenheit. Water freezes at 32 degrees Fahrenheit. Thank you for that totally random number. Water boils at 212, also another totally strange number. 0 degrees Fahrenheit, if you wonder, well, what's 0 degrees Fahrenheit? That's the freezing point of a concentrated saltwater solution. Again, why? Who knows? We like Celsius. Celsius is much neater. Celsius, water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. And the difference between those two is a nice even 100-degree scale. Kelvin has the same shift or scale as Celsius. You just add 273. So water freezes at 273 degrees Kelvin and water boils at 373 degrees Kelvin. So whatever your Celsius is, if you want to get it into Kelvin, just add 273. Why do we do that? Why do we have a Kelvin scale? Well, the Kelvin scale shifts all the known temperatures over so that they're a positive number, so that we don't have a negative temperature. Like, you know, when it's negative 15 degrees outside, negative 15 degrees Fahrenheit, or it's negative 2 degrees Celsius. What is temperature measuring? Temperature is measuring thermal energy. It's the vibration of something. How can you have a negative vibration? So we can use those other temperatures, but in certain math problems, we don't like to have a negative temperature. So Kelvin takes care of that. At 0 degrees Kelvin, that is known as absolute zero. Absolute zero is when let's see where they have it. No, they don't have it in here. Well, we talk about it a little bit later, but absolute zero, here it is the coldest temperature that we can get in the universe. It's when all motion of molecules virtually stops. Okay, it's when all the vibration that's happening in molecules just doesn't exist anymore. In order to calculate temperature, you want to have equations. Again, on your in your lab manual in the back, there's a formula sheet. That's a useful formula sheet, and you can just add things to the back of that if you want. The two equations here should be on there, maybe not exactly like this, but two formulas to get you from Celsius to Fahrenheit. So, you know, if I want to go from Celsius to Kelvin, I add 273. Here they have 273.15. If you don't want to use the 1.5 or 0.15, that's okay. You don't have to. Celsius is Fahrenheit minus 32 over 1.8. So you want to be able to jump between Fahrenheit and Celsius and Kelvin and Celsius. There's not really a nifty way to go from Fahrenheit to Kelvin. Oops, sorry there. Not really an easy way yet to go to Fahrenheit from Kelvin. If you're given Fahrenheit and you want Kelvin, you kind of have to pit stop in Celsius and then go to Kelvin from there. So we'll do one, okay? It is a delicious 76 degrees Fahrenheit outside. Okay, but your European friend is here and they have no idea what that means. So I want you to convert that to degrees Celsius. And then let's say you want to do a math problem with it later and it needs to be in Kelvin. So then convert it into Kelvin. Okay, I'll give you guys, I don't know, a minute and a half for that. Hey, I lost you guys for a second. Are you guys, can you hear me now? Is everything okay? Yeah, okay, cool. Sorry, my internet's whatever, life, pandemic is what it is. So we were temperaturing. I remember we said what, 76? So we have 76 degrees Celsius. So no, Fahrenheit. And we want to figure out Celsius. So I'm going to put the 76 right in here. Now, the way that this equation is set up, you need to do the subtraction first. So you take 76 minus 32 and then divide it by 1.8. And that is approximately 24 degrees Celsius. So for somebody in Europe, they would hear something like 24 degrees Celsius. That would mean a nice day, right? For us, that sounds cold, but it's not. If we wanted to convert this to Kelvin, I would take this here and I'm just going to add 273 plus 273. I'm going to tell you right now, my care on sig figs for temperature is like non-existent. So don't stress too much about it. Okay. This is approximately 297 Kelvin. Kelvin doesn't get a little degree too. Just know that. Yeah. So you guys, do we need to do more of those? I feel like that's not bad. Okay. So have the equations handy when you take your test. There's some more things that have the word heat in them that don't Mean temperature. So temperature is the measurement of thermal energy. Heat is the transfer of energy from one thing to another. Then we have this thing called heat capacity. Heat capacity is the quantity of heat, usually in joules, required to change the temperature of a given amount of a substance by 1 degree Celsius. We don't use heat capacity a whole bunch, but we do use this other thing called specific heat capacity, which is sort of more detailed. Specific heat capacity is the amount of heat required to raise a certain amount of material a certain temperature. Specific heat capacity is going to have funky units. Okay, it's usually going to be written as joules per gram degree Celsius. So the unit is joule over gram degree Celsius. Or sometimes you'll see it as calorie per gram degree Celsius. Okay, or sometimes you might see it as joule per gram per gram Kelvin. Really, for this class, we kind of just stick here. Okay, I don't get into calorie per gram degree Celsius. So it's a funky unit, 3 units for specific heat. Every material out there has its own specific heat capacity. You can like look them up in an appendix. You don't need to have the specific heats memorized except for water. Okay, here's water. Water's specific heat capacity is 4.184 joule per gram degree Celsius. Remember that number from before? What does 1 calorie equal? 1 little c calorie equals 4.184 joules. There, so we see that number repeated again. And so do know the specific heat of water. Look at these specific heats of all these materials. Lead, gold, all these things have really low specific heat capacities compared to ethanol and then water. Water requires so much energy to heat up. And you may be thinking, well, you know, but it has to be really, really hot to melt lead. It doesn't have to be really hot to melt water. That is true. But lead, if I have a gram of lead and I have a gram of water, it is easier to heat up a gram of lead than it is to heat up a gram of water. It takes less energy to heat up a gram of lead than it does a gram of water. Real life example. When you are heating up a pot of water, let's say it's a copper pot, how quickly does the pot get hot? Pretty fast. How quickly does the water get hot? It feels like it takes forever sometimes. It's because there's so much energy that needs to get pumped into each gram of that water to raise it up to its boiling point. So all these things come together in this equation. And again, that formula sheet that you have in the back of your lab manual has this equation, Q equals MCAT. Sometimes you'll see it written as a capital Q, Q equals MC delta T. Sometimes you'll see the C as an SH. You'll see it as Q equals M times SH times delta T, SH for specific heat. Okay, I like Q equals MCAT. So what do each of these things mean? Well, we've got an equation here and we have 4 variables. 1, 2, 3, 4. So in a heat capacity, specific heat capacity problem, I would give you 3 of the 4 variables, right? And you would have to solve for the 4th. I could give you all of these and you solve for heat. I could give you this and this and this, and you have to solve for the temperature change, whatever. Q is going to be the amount of heat in joules. All right, so when we hear energy, heat, a joule value, that's going to be Q. That's the amount of energy flowing in or out of the system. Now, it is important to note that Q can be plus or Q can be minus. So we could have a negative number here. If energy is flowing out of the system, it's losing energy, it's minus. If it's flowing in, it's positive. M is going to be mass, and you want this to be in units of grams. Okay, C is going to be the specific heat capacity, and this is in joule per gram degree Celsius. If this funky unit is in joule gram degree Celsius, everything else has to be in units to match that up. Remember, we can't use an equation and have different units, just like with density. Density equals mass over volume, right? If your density is in gram per milliliter, your mass needs to be in gram, your volume needs to be in milliliter. So if this is in joules per gram degree Celsius, well, energy needs to be joules, mass needs to be grams, and then temperature needs to be in Celsius. Now it's not just temperature, it's delta T. This delta symbol means change in. So delta T is equal to your final temperature minus your initial temperature. If your final temperature is bigger than your initial temperature, you'll end up with a positive number and your Q will be positive. If your final temperature is smaller, you get colder, this will be negative and then your Q will be negative. So it is okay to have negative numbers in this. If I gave you information in like kilograms, convert it to grams. If I give you Q in calories, convert it to joules. Make sure you match your specific heat numbers. Okay, so you get 4 variables, well, really 5 because this is 2, right? It's a temperature and a temperature, and you have to subtract them, but that's pretty easy. So let me give you a variable, isolated variable triangle thingy majigger. Put it in a second. All right, so for Q equals MCAT, when isolating variables, it can be easy to have this here. So draw a triangle, cut it in half, and then in the lower half, cut it into thirds. On the top, put the Q. On the bottom, put the M, then the C, and then the delta T. And just like with the density triangle I gave you, this is a divisor, and these are multipliers. So it's a fast way to isolate variables. Q equals mass times C times T, right? Mass times C times delta T. We already know that one. Well, what if I want to find C, my specific heat? C will equal Q divided by mass times temperature. Okay. Let's say we want to solve for mass. Mass is going to equal Q divided by, right, that's their divider line, C times T, C times delta T. That's just like one way to isolate variables. If you're good at isolating variables and you can look at this and just isolate from that equation, just use that. You don't have to worry about the triangle. That's just a spatial way for some people to get isolating a variable. So let's do a problem with this. Let's say, look at this here. So gallium is a solid at 25 degrees Celsius, and it melts at 29.9 degrees Celsius. If you hold gallium in your hand, it can melt from your body heat. How much heat must 2.5 grams of gallium absorb from your hand to raise its temperature from 25 degrees Celsius to 29.9 degrees Celsius? The specific heat capacity of gallium is 0.372 joules per gram degree Celsius. Okay, so anytime you start seeing specific heat capacity, heat, temperature changes, I would just write out Q equals MC delta T. Chances are that's the equation you're going to use for it. Now we want to organize our information here into what's given and what we're trying to find. So for this problem, it's saying how much heat. That's what we're trying to find. Now, so often I have students get Q, which is heat, mixed up with C, which is specific heat capacity. Don't mix those two up, okay? Q is in unit of joule. That's our heat. C is specific heat capacity. That's funky unit. That's joule per gram degree Celsius, all right? This value changes depending on the other things. C is consistent for whatever the material is. So we want to find heat. So we want to find Q. That means we better have information on all the other stuff. Do we have the mass? Yeah, we do. It's 2.5 grams. Do we have the specific heat? Yeah, they throw it in at the very end. They say, here's the specific heat. It's 0.372 0.372 joules per gram degrees Celsius. And do we have the temperature change? Almost. We know the final and the initial, so you have to do a little calculation. We want to end at 29.9 degrees Celsius, and we start at 25 degrees Celsius, 25 degrees Celsius, 25.0 degrees Celsius. So what is our difference? 4.1, 4.9, yeah. 4.9 degree Celsius is our temperature change. So we have everything we need. We just plug it in. Q equals mc times delta T. So my mass. And when you're plugging this stuff in, use all the units. Okay, use all the units. Don't just write numbers because then we can see what cancels. So 2.5 grams times the specific heat, which is 0.372 joule per gram degree Celsius, times the change in temperature, which is 4.9 degrees Celsius. Now I can look at my units and see what cancels. Look, Celsius cancels, gram cancels. And what unit are we left with? We're left with a unit of joule, which is a great unit to have for heat, right? We want it in joule or calorie. So we multiply those together, 2.5 times the 0.372 times 4.9. And I get a value of 4. Just two sig figs, so 4.5, and the unit on it is a joule. So it takes 4.5 joules to raise 2.5 grams of gallium from 29.9 degrees Celsius to 25 degrees Celsius. So these problems with specific heat are not dimensional analysis problems unless you have to do an initial conversion. They are plug and chug, right? You have an equation, you need to plug and chug it in. 4.6, what did I say? 4.5? Okay, I did. Time 0.372. I do something wrong here. I must have forgot a decimal. 0.372 times. Oh, I just didn't round correctly. Okay, I said, what did I say? 4.5, 4.6. All right, let's do, I want you guys to do a problem. So there's a nice worksheet in our Moodle page. And again, remember, these worksheets are not something you have to turn in. They are just to provide you with more example problems. There's the little triangle, Q, M, C, delta T. All right, I want you to do number 2 and number 3. Let me try and zoom in here a little more. There we go. Okay. So number 2 is how many joules of heat are needed to raise temperature of 10 grams of aluminum from 22 to 55. The specific heat is 0.9. Okay. That one's very similar to the one we just did. Number 3, calculate the specific heat capacity. This one's a little bit different. All right. It's wanting specific heat capacity. So you're going to have to isolate variables. So I'm going to give you all 5 minutes to work through both of those. And then we'll come back together. Go over them. And then you guys are like almost done. Okay, because it's like the end of the chapter. So right, so for this first one here, this is a similar setup. Q equals mc delta T. We're trying to find Q in joules. So we need the mass. The mass is 10 grams. So 10 grams. The specific heat is funky unit guy over here. So 0.90 joules per gram degree Celsius. And the change in temperature is the final minus the initial. So 55 minus 22, which would give us 33 degrees Celsius. Celsius goes away, gram goes away, and we're left with just unit of the joules. And 10 times 0.9 times 33, 297. Really, we only get 2 sig figs, so I would round it to 2 sig figs. 297 would become 300, and the unit on that is joule. Second one, a little bit different because instead of solving for Q, we want to solve for C. So C should equal Q over M times delta T. So you should have a value for Q in energy, which is joules, and that's this thing right here, this 67,500, that's my Q value. 67,500 joules. Do I have a mass value? I better. It's right here, 1,500 grams. So divide this by 1,500 grams. And then temperature is also on the bottom, will really change in temperature. Our ending temperature is 57. We subtract from the beginning temperature, 32, and we get a 25 degrees Celsius, 25 degrees Celsius. So we're going to take that 67,500, divide it by 1,500. You can equal it out and then divide it by 25. Or if you want, you can multiply these and then take this number and divide those two and multiply. But both of those are under the fraction bar. I end up getting 1.8. And if you notice, none of the units cancel, which is a good thing. We want funky units. Joules per gram degree Celsius. All of them stick around because we're finding specific heat. And specific heat's the funky unit. Questions on that? Plug and chug. The only time that you might get tripped up is if they give you the information in a unit that doesn't match. So if this, instead of saying 1,500 grams, said 1,500 kilograms, make sure you first get it into grams, then plug it into the equation, okay? Same thing here. If this is in joule per gram degree Celsius and they give you the joule value in calories, convert from calories into joules and then plug it in. Okay? Because these equations don't work if they're in different units. Internet, you're unstable. What's going on? Okay, so that, let's see what else is going on in here. Pretty sure. That's the end of, yeah, that's the end of chapter 3. So we end with just those calculations. So definitely get the mastering chemistry homework in because there's a lot of practice with these in like non-conventional ways. So it challenges you. Sometimes people will go, oh my God, the mastering chemistry is so hard. Are the tests going to be this hard? No, I would say my tests are not as hard as the mastering chemistry. Okay. Which means it's good to practice that because that will, you know, push your skills and then hopefully you come back and take the exam and it's not quite as tough. Your first exam is not next week, but the following Sunday, Monday. So do take a peek at the syllabus and make sure you've just got that available. We have one more lecture next week. We'll do chapter 4 to finish up the information for the first test. Yeah, that's all I formally have for you guys. If you have any questions, feel free to stay around. Otherwise, enjoy your week. And I will see you next Wednesday. Yeah, but I'm here though. So if you need something, just let me know. Bye, guys.